Well, hello everybody. It's 3 p.m. on the third Thursday of February 2026, and I welcome you all to the 18th episode of our 3D Thursday webinar series. It's great to have some of you online already, and while the others join, I'll take a few minutes to introduce the topic of the day and also our speaker of the day. I hope you're all as excited as I am to dive into the ever evolving world of additive manufacturing. Okay. We are focusing on an exciting topic, opportunities and challenges of cold spray additive manufacturing. This webinar explores how cold spray technology, being used for quite some time now for surface coating applications, has evolved over the last few decades into cold spray additive manufacturing, also known as CSAM. It's a high rate solid state additive manufacturing process that enables the rapid fabrication of near net shape components. While CSAM offers distinct advantages over conventional AM techniques, it also presents specific challenges, and that's what we'll be discussing today. There is a dedicated Q&A sessions at the end, but we would love for the session to be interactive. So please drop in your questions at any time in the chat box. So I repeat again, in the chat feature, the Q&A feature is not enabled. So please leave your questions on the chat box. And we will try and collect the questions together and ask the questions whenever relevant. Today's webinar is being recorded for learning purposes. By participating, you agree to the recording and distribution within our learning community. Now it's my pleasure to introduce our speaker for today, Dr. Suresh Palanisamy, Director, Manufacturing Futures Research Platform at Swinburne University of Technology. Dr. Suresh Palanisamy is the director of the Manufacturing Futures Research Platform and the professor of advanced manufacturing leading research in metal additive manufacturing. He has been the chair of Innovation Task Force in Additive Manufacturing CRC. He was the founding director of Transport Innovation Center, working closely with the Malaysia Automotive, Robotics and IoT Institute and Industry for 3+ years. Alongside this role, Professor Palanisamy had also led a $26 million Air Platforms program in the Defense Materials Technology Center, DMTC, for 7 years, and serving as a project leader on a number of key research projects. Professor Palanisamy has played a key role in engaging with more than 70 industries and 20 research partners across Australia and internationally. He has won a number of awards nationally and internationally with his industry partners. Dr. Suresh, we're excited to have you share your knowledge and experiences with us, and special thanks for joining in late in the evening from Australia. So over to you.
Thanks. Once again, thank you. I'm just about to share my screen. Just bear with me.
Mm-hmm.
I hope you can all see my screen now.
Yes, your screen is up.
Wonderful. Thanks once again. I could see some of my colleagues from Australia also joined. So it's nice to see them also from late evening in Australia, and also all those joined from India also. It's a great opportunity to present and talk about the cold spray additive manufacturing capabilities and challenges, I would say. And as introduced, I'm the Suresh Palanisamy. I'm the director of Manufacturing Futures Research Platform, and also I'm chair of Innovation Task Force at AMCRC. I'll talk about both this institute, a little bit of background, probably in a couple of minutes. Quickly, I go through this institute, so it'll give a bit of idea. So just before, for those people who don't know where is Swinburne, so I'm not sure, unfortunately, I couldn't get a clear image. This is a well-known photo, well-known image of a lot of people, cricket fans might know. This is a MCG ground And Swinburne is, I would say, not far from that, probably a few kilometers from MCG. So that's just to show you from Melbourne Cricket Ground, not far. Swinburne is not far from MCG. We are part of the eastern suburbs in Melbourne. So that is where Swinburne is located at. So just to give a perspective of where in Australia I'm dialing in or talking to you. So quick outline on today's talk is, as I mentioned, I'll briefly give you an overview of my role or what I do. That gives a bit of appreciation of what I'm going to talk about. So mainly I'll talk about metal additive manufacturing, obviously cold spray additive manufacturing. That's the topic of the day today. And obviously some of the research is related to cold spray additive manufacturing. So Swinburne University, there is a number of institutes out there, innovative platform, MedTech Institute, and just bear with me. A number of institutes are there, and manufacturing future research platform is there, like a cog in the wheel. So we work with number of researchers from different areas, from space to aerospace, innovative planet, and MedTech and health innovation section. And we have two key facilities part of that. One of them is the Factory of Future and Swinburne CSO Industry 4.0 Test Lab that is mainly focused on composites, additive or laying up of composite structures, and automated Industry 4.0 Test Lab facility. It's a unique facility which is in Australia. And we also have 5 programs, briefly I mentioned about them. So the 5 programs are related to Industry 4.0, AI, machine learning, intelligent robotics, digital design, net zero carbon processes. So this is all led by professors from across the university, from different schools and different departments. And Professor Dimitrios, Associate Professor Haley Wong, Professor Mats Isaacson, Boris, and Professor Akbar, they all lead the respective areas, and they also lead their own center and activities, research activities. So we work across verticals and horizontals in different areas in this area. So this is what I look after. This is all the people involved in my manufacturing research platform, I would say, in Swinburne. So as I mentioned, there's another role also I do, which is additive manufacturing, Cooperative Research Center. CRC stands for Cooperative Research Center. That is one of the unique Australian government, federal government funding for past 35 plus years. They've been funding different CRCs. So additive manufacturing is one of the recent CRC that's got funded by the federal government. So the key part is, since we're talking about additive manufacturing or cold spray additive manufacturing, so this is one of the key centers in which quite a lot of work will be carried out. So we've got funding 57.5 million from the Commonwealth federal government, and we'll be working on for the next 7 years. And obviously we got funding from the industry partners also, total of $270 million with 77 industry partners, 5 government bodies, and also 13 plus 14 plus research organizations. So from the perspective of Indian currencies, you can see 57.5 million is roughly equivalent to 370 crores over a 7 years period. And again, 17.3 billion, again in NRI for the 270 million roughly over a 7 year period. So what we do is probably working with the industries, as I mentioned, industry-led activity, collaborative research, supporting with Australian industries, and also globally, we'll work with globally also. I'll talk about some of the companies in the global space and mainly focused on a number of areas, mainly taking the work from TRL 4 to 7 or technology readiness level, or NASA's technology readiness level from 4 to 7, working in the valley of death kind of area. So also building long-term collaborative partnership with research and industry bodies. As I said, these are the 77 small to medium and large businesses, 13 research partners and CSRO like CSR in India. CSR also part of this. And we have a number of international partners, including Boeing as a major partner here. And SMR Automotive, probably from India. So some of you might know about this company also, based in India. We also work with them. And obviously we work with ASTM and quite a lot of other international bodies, EOS machine manufacturer, Trump also machine manufacturer, additive manufacturing machine manufacturer. So these are the leading universities that are working in this space in additive manufacturing. And specifically, I'll talk about mostly with Titomic and P3. Those are the local Australian companies. They work or they manufacture equipments in cold spray technology, based technology, and also work with Rosebank Engineering, another company which uses the cold spray technology here in Australia. So the programs are sustainable manufacturing, that is a core program, and application and materials development, technology and process development, surface technology, and post-processing. These are all the key areas, I would say, for any additive manufacturing technologies to look at. So just going into the topic, and I've taken a bit more time than expected. So I'll talk about metal additive manufacturing specifically, why and where, how, and it's been useful for. So probably when I talk about metal additive manufacturing, general knowledge is about, always we talk about net shape or 3D manufacturing, full form of manufacturing, close to finished part kind of thing, where quite a number of technologies are used. At the same time, we also mentioned about sustainment and processing. When I say processing, coating like small micron thickness, so I would like to refer this millimeters to meters. You can call it as manufacturing. Sustainment means microns to millimeter, and coating means nano to micron range kind of thing. As you can see, the cold spray has been useful for all different kind of manufacturing process. And also you can see different technologies: laser-based deposition, electron beam melting, wire arc additive manufacturing, selective laser manufacturing. So quite a number of manufacturing technologies are there in near net shape area, but however, very less and less in the coating and sustainment area. So we are talking about, this is the area where cold spray commands was started with, but however, you can see it's a wide spectrum of applications that cold spray technology can be useful for. And this is the area which I will focus mainly on, I would say. But some of the applications, some of the work which we have done also in the sustainment area of cold spray. So when you talk about metal additive manufacturing, obviously powder bed based, this is the powder bed based. So the building rate and versus the build size, you can see microns to millimeters. So it's barely touches meters because the size of the bed determines how big the parts can be manufactured. However, the DED, direct energy deposition, or blown powder type here, which can range from millimeters to meters easily, and AFSD, additive friction stir welding, stir deposition process, as you know, which is also fast deposition, high rate per deposition, and it can go up to meters or to large scale level. It's the constraint is again the machine size. So the cold spray process sits somewhere in between DED and additive friction stir welding or a deposition process. Again, it sits, you can manufacture from millimeters to meters range of additive manufacturing, and it can go up to the size of the machine also is a constraint, but some cases large scale machines can be manufactured also. So specifically talking about cold spray additive manufacturing. So the cold spray technology has been around for a number of years, actually a few decades, I would say. And it started as a thermal spray process. And you can see there's different thermal spray process technologies are there. The cold spray sits at the low end or the bottom end here because the temperature range, the gas temperature range is low, very low temperature range. It's used. And however, the particle or the gas deposition or the gas temperature, as you can see, thermal spray, this area is quite high. And that is where HVF also is there, and thermal spray technologies, quite a lot of thermal spray technologies are used for hard metal coating applications, ceramic or a few different high temperature, high melting point temperature materials to be used in this area. However, so this area, the cold spray is the process where you don't heat the powder particles, because usually thermal spray, the powder particle is heated and with high temperature with the gases used. That is how they're propelled. And again, this diagram is a different diagram to the same one I showed you earlier. So the solid state, main thing is the solid state particle deposition, bonding via particle plastic deformation, and rapid coating, repair, and near net shape manufacturing also. So I'll talk more in detail about each of these steps in the following slides in more detail. So this is what I was trying to mention earlier. That's the compressed gas, you can see it goes in one direction with each helium and nitrogen, for example, and it can heat the powder particles comes from the different hopper and fin through the nozzle, which is the like convergent divergent nozzle, which can able to propel the particles at the higher temperature and high pressure also, as you can see here in this particular case. And the velocity ranges also differs depending on the gases you use. For example, if you are using inert gases with high pressure, which is obviously 7 bars to 40 bars range or more than that, and also the temperature can be high, also the velocity can be high, velocity can be achieved. So in this case, mostly 3D printing and coating and repair application can be useful for this particular case. So most of the work which I'll be talking will be in this particular area because that's the equipment we have. High pressure air-based cold spray system. So that's the system which we have, and that's what most of my talk will be related to that particular area. Again, talking about additive manufacturing cold spray process, the cold spray was mostly applied until last 10 to 15 years ago for sustainment, which I showed you earlier. That's one of the slides. So just millimeters, microns to millimeter thickness. So sustainment or coating applications, basically, that's where it started with. However, with the technology advancement and also the slicing of the software technology that's used by one of the participant company here, Speed 3D, and they can able to move the robotic arm and slice the slice the CAD file such a way that automatic slicing is done and tool path generation is obtained on this robotic arm here. And the nozzle is fixed. However, the robotic arm moves around so that it can able to build the parts. I'll show you a video later. Then you can see that that will give a better understanding of that. As I said, particle deformation and bonding with high velocity impact, no melting at all, and solid state powder compaction process. Again, I'll talk more in detail about in the next few slides. So the advantages, when you're looking at the cost-wise, how does it look compared to the other system, cold spray systems? Because air-based cold spray this is here, high pressure air-based cold spray system. This is where it is here, and argon, helium, and different gases are there. So you can see the variation with the helium, obviously. The cost of the inert gas is high. Obviously, the normalized cost is very high compared to the other cost of other gas or air-based systems, I would say. And also the low pressure system is very comparatively cheaper because of the application areas where it is used, and also less need of a high temperature or high compressed air in that case. So that's what you can see the size or the dimension of the equipment. This low pressure can be very small, half a meter to meter kind of thing. It's a portable system, some cases. And obviously with high pressure system, you need to have a large enclosed section to avoid any damage to the external environmental place. So that's why the cost also varies comparatively with the low pressure system, which can be mobile and taken on site for repair and different applications, coating applications. So the bonding mechanism is also varies based on the type of whether you're using gases or low pressure or high pressure. That also varies quite a lot. So as you can see, the modes of mechanical interlocking might change, and the extrusion of the substrate happening, and also embedding of the particles, the bonding part, the particles also happens to the substrate. So this is what again, you can see that in the micrograph here, aluminum, that is titanium on top, on the aluminum oxide or the coating on the bottom substrate, different core substrate. Again, similarly here, copper on the top and aluminum on the substrate here. So you can see the aluminum extruding or extrusion into the powder particle, and also the embedment of copper on the substrate. Mechanical interlocking happens, and also adiabatic shear instability is one of the main mode of bonding mechanism, also metallic bonding also. Again, with high pressure cold spray, mechanical interlocking with adiabatic shear instability makes it more stronger, a better bonding mechanism. And air-based cold spray system, mostly the mechanical interlocking happens. So again, that is different, quite a number of different modes of bonding mechanisms are there. And especially depending on which application, which method you are using, as you can see, the dotted lines and also the lines, solid lines shows the different parameters of different conditions. And with jetting, material interface, grain refinements, quite a lot of materials and mechanical interlocking happens structure-wise. Changes can also happen. This is just a concept map. Yeah,
Yeah. Dr. Suresh, there were two questions related to what you just discussed, so I thought I'd quickly take the chance to answer them. The first one is how does particle velocity impact bonding in CSAM? So we just went through the slide that the velocity does impact adiabatic shear instability and cause better bonding. But is there
yeah.
like a upper limit after which the velocity may not play a role in the bonding?
Absolutely. That's a very important question, I would say, because the nozzle dimension, the nozzle pressure, the design, that is a
Mm-hmm.
limit is there. So because as you can see, I'm not showing the nozzle design very much I'm not going to talk much about nozzle design because that is itself a vast, big topic, I would say. But again, that plays a major role in that sense. And also the velocity is obviously when you're having using the gas, different temperature, different gas that can able to propel the particles with a more with the temperature, higher temperature also, at the same the higher velocity also. But the range, that is where the range is critical, and depending on the material and also depending on the substrate you are using, that will
Mm-hmm.
vary because you don't want to use high temperature with the polymer application or composite materials. But however, you want to use high temperature for steels and other titanium and other materials which have high melting point. So that's the dimension of the nozzle plays a major role also in that.
Okay, so I think you kind of answered another question which says what are the key process parameters? So I think it's the nozzle design, temperature, velocity, the substrate material.
Yeah.
Would you like to add another few?
And again, powder particle is also one of the major parameter, I would say, because the particle size, the dimension, that also plays a major role. And it's a certain range, powder particle range also varies. That also is a parameter, or that's also you have to consider that as a factor also. But exactly all these parameters are critical, including the gas, pressure, temperature, and velocity. It's all interrelated, all of them,
Mhm.
but also at the same time, it plays a major role in that.
Perfect. We'll let you continue, doctor.
All right. So that's very important and important question to understand because again, the properties wise, you'll see a significant difference in the properties because using the inert gases and using higher temperature, the bonding mechanism is far more better, and the properties also better properties you can achieve. However, cost again, that's the graph or one of the graph I showed you here. So you're obviously looking at the normalized cost factor, also critical thing. So how much again, as I said, helium provides a better property. However, the cost factor is high comparatively. So what you need to trade off something, whether you can achieve the properties down the track, you can do post heat treatment or post processing, the latest stage. That is the additional step that is involved when you finished manufacturing or deposition. However, with the helium, you don't need to do additional steps post processing of further heat treatment or anything. In some cases, not in always. Some cases you don't need to do it. But for air-based cold spray, even because of the cost is low and the properties might not be that great, surely you need to do post processing. That I'll talk about that also later stage. So this is the process that I'm talking about. The Speed 3D is Australian manufacturing company, and that's what I was talking about so far. And there's some of the parts that we printed. That's examples are shown here: electronic console box and pipe fitting. So this is the actual application. This was used in one of the Australian Navy vessels, boats, petrol boats. Without this camlock device, this coupling device, this is the hose this connects with the hose on the top of the dock of the ship. Basically, they try to wash the salt water away. If this is not available, this is not functioning properly, then the boat cannot go into the water at all, the sea at all. So they have to wait until this is fixed. So it takes the time factor to get. Sometimes if the part is not readily available, it may take some weeks also. But in this case, it can be done in a day or two straight away, manufactured, designed, sorry, obviously the design available, manufacturing it, machining it, heat treating it, all done in within a day or two. Then the ship boat can go back into the sea again. So these are the small small things like that makes a big difference in the application wise. So just bear with me. That might be the video might be a little bit loud. Uh, just be mindful of the volume you have. It's nothing. It's nothing. The robotic arms moving. So as I said, the slicing software works, and the slicing software enables the robotic arm to the converts into the G code of the robot, and that enables the robot arm to move in a way, such a way that the part can be built over a period of time. And again, as you can see the part, the team Nirvana and Rizwan, my team here, and they're holding the part, one of the parts that is manufactured. This is a copper part here, and I'll show a few more parts later also. For example, this is one of the examples, another example, just a cam lock part, which I mentioned earlier. This is a similar sort of part, which set design time roughly 1 hour, print time 30 minutes roughly. And obviously, when I say cook and cut, there's machining and like heat treatment process. Sometimes it's taking 17 hours and machining time was 2 hours. As I said, that's what within a day or two, you can get the parts completed and ready to be used on the boat or any particular application that might be required. So this is how this is the twin speed 3D software. This is how you see the slicing software, and you can visualize the simulation can be done like a digital twin. Simulation can be done, then that can be visualized before you go on start printing the part also. Sometimes it takes obviously more than 1 hour in some cases, yeah. So this machine, what we have is roughly can print up to 4 kilograms. The diameter can be 350 by 300 millimeter height. And in this particular case, is an example which we worked with the defense partner, and it can able to. The main application is aluminum silicate tiles. Tiles are shown here. Ceramic tiles are shown here for thermoelectric material deposition or development. We use copper to coat the tiles as shown here. For this is a part of a thermoelectric generator, converts waste heat into electricity, and electricity as a co-generator potentially reduces heat signature of naval platforms or any particular application. So this is the example, but obviously adding copper to it, the ceramic tile, it obviously enables far more better heat transfer. And also the ceramic tiles are made up of rare earth materials, so it's also toxic materials also. So it's avoid the application or usage of rare earth materials. It can be better using copper as a material for the thermoelectric generator. That's an example here. That's one of the examples shown here. I'll talk about quite a lot in this particular case study. And another example here, this is a coating. This is not really a cold spray additive manufacturing process, but during COVID times, when obviously the virus, COVID virus, can be carried on the substrate, any hospital or anywhere, any substrates are that can be touched by the patients or the people who got virus. For example, here the stainless steel, the COVID virus, we published a work on this. It can last for 96 hours, quite a few days, and we can coat the copper coating it and polished copper coating. It can the virus lasts only less than 24 hours or something like that. So that means the virus, because of copper's nature, probably all of you know the copper utensils that we use for a number of years, that is obviously has the antimicrobial properties, antiviral properties. It kills the viruses very soon. So taking the existing, this is a part of a toilet door push plate. It's called push plate here, and we use the toilet push plate here. Just taking it out and coating it and reusing it. For example, as you can see, this is again replaced in the toilet door here. That avoids the contact surfaces where it can kill the virus very quickly, as you can see in this particular graph here. Obviously, the another case is again looking at the different orientation of build direction. So this is a build direction on the y direction here, xy direction here. Comparatively, the z direction build, where vertical build, there is quite a few different properties can be seen through different build direction also. So that's again the work. Yes.
Yes, Dr. Suresh. So there were a couple of questions on materials. I thought we can take it.
Yes. Yeah.
Yeah. So the first question is definitely on the different materials that today can be used with this technology. But in specific, the question is, can we print D2 and M2 tool steels?
I I don't think we can do the D2 or M2 tool steels. Need to check on that because this particular system, because of the temperature range, we cannot do that. But we have been trying to do with the 316 stainless steel material, and also
Mhm,
we are trying to do 15.5 pH and 17.4 pH materials.
mhm,
So because the temperature range in which we operate, some of the conditions is not possible. But
mhm,
however, uh, in this particular case, the equipment which we have, we can able to print copper, aluminum, uh, nickel, aluminum, and copper, bronze materials, and also stainless steel materials. And
mhm.
titanium is possible to print titanium also up to some certain extent. So these are some limitations with this technology. Yes, not all the materials might not be possible, but however, some of the highly reflective materials like copper, when you have a laser-based system to print, copper
Right.
is quite reflective and aluminum also quite reflective. Some of the materials like that that
Mm,
cannot be printed in normal technology can be used in cold spray because it's a solid state. You're not melting the particle. That's one of the reason.
mhm,
However, the properties wise to achieve the right properties, it's still a challenge there. That's what I'll show you the properties wise how the variations looks like. And
mhm,
most probably you can achieve the properties similar to casting properties.
mm. Okay. So you just also went through a slide where you deposited copper over ceramic, and in the
Yeah.
chat box we do have a question on what are the limitations regarding material combinations in terms of multi-material builds. So if you
I'll
could put some light on
sure.
that.
So that's another interesting question. I'll talk about it because we are working on the multi-material application. So I'll have some of the slides later stage. I'll talk more in detail about that later stage.
Perfect.
Yeah,
We let you continue.
sure. Thanks. So that's what this are some of the early studies which we done. And again, when I talk about most of the work was done in aluminum 6061 material, aluminum 6000 series, I would say. So horizontal build, again, vertical build. So that's good to see that's quite a different properties are achieved the different conditions. And also heat treated, when I say heat treated condition, this is the wrought properties compared to the heat treated properties, as you can see, as built condition, you're not achieving significant tensile strength. But obviously, once it's heat treated, you can see the significant variation is the tensile strength and also the other properties as much corrosion properties also that changes also. So it because corrosion properties are a bit far more better, I would say, with regarding to the the heat treated conditions, cold spray particles, cold spray parts, and also the uh, parts that is heat treated close to the wrought material conditions. That's what again I should say. This is close to the casting properties. What we can achieve is the casting properties. So you're looking at the replacing of some of the casting parts. This is potentially possible. But volume wise, again, one of the challenges with additive manufacturing, as all most of you know, that increase when you go with higher volume, then the cost trade-off is there. It's always which whether to go with casting or machining process. It's always a challenge. So that is why we always say in additive manufacturing sector, design for additive manufacturing is critical. If you can only design certain parts that has additive manufacturing features, then it's obviously only can be made via additive manufacturing process. All right. So in some cases, it's not viable to make the machine parts or cast parts completely into cold spray parts. But for example, in the example I showed you with the cam lock fitting and also some of the console boxes, which you can have multi-material some cases, that is far more beneficial, which cannot be achieved through any other process. And again, this slide shows again the powder particle deposition point of view, high pressure with the cold spray. Again, as you can see with high pressure system here, you can see the dense layer formation is that addition layer, and also you can see different layer formations are happening with the low pressure. You can see it's not as dense as the high pressure system. So, and also the particle because of the velocity at which it's propelled, you can see the shape of the particles also looks different. And obviously, people tend to say inverted blobfish kind of look it has. So that's why, again, the particle looks like a parachute shape, like upside down blobfish, and also the particle fusion happens. Grain refinement is also possible with high pressure system compared to the elongated particles, and particle boundary conditions is also looks at like that, and grain elongation. So mostly elongated this way and horizontally when the particle shapes, or you can see the dense mechanism of the bonding mechanism. That clearly shows the property wise why the better properties can be achieved with high pressure cold spray system. And again, I've spoken already about anisotropy here already with the copper. So the annealing temperature we used is 400 degrees centigrade and sintering around 1000 degrees centigrade. That's the temperature range we used there. And obviously the propellant gas pressure was 30 bar pressure, and the gas temperature was 425 degrees centigrade in this case. When I say the build direction wise, you can see the vertical build always happens. When it goes to the edges of the print part, you can see the robotic arm inclines and forms a 45-degree build angle. So some cases this was an issue initially. So we have to machine off the excess materials. We build excess parts, so we only take the middle section where the properties are far more better. Though, because otherwise some sort of crack formation happens in this particular boundary section. And that was visible in the early studies also, when we looked at it. Again, bulk copper, and also compared with copper heat treated condition, and different heat treatment conditions are done. So this is again for the study on a different substrate, viral properties, looking at viral properties of the virus, which can stay or which can quickly die off in the certain substrate with a stainless steel substrate and also aluminum substrate. Both at the heat treated condition and has built condition was studied in detail. So multi-material, interestingly, somebody was asking earlier about metal matrix. Here we call it metal matrix composites kind of thing. So copper incorporated with the graphene particles, just 0.5% of the weight, or 1% itself is enough for graphene to be mixed with copper particles and deposited. And we can see that it gives a better thermal conductivity point of view. The Seebeck coefficient is far more better, and it gives a thermal conductivity also far more better when you compare to use with graphene copper material, and different conditions, different properties better properties can be achieved. But however, printability and thermal, still quite a lot of work needs to be done. People are interested to look at it. As I said, you can see 0.5% of graphene powder. That takes quite a lot of the areas or sections, and it can it will form a different shape or different form, and you can see that particle graphene embedded into the copper deposits here. And aluminum bronze material, as I said, aluminum and copper, aluminum bronze material, again, using different process of sintering process used, again, 90% copper, 10% aluminum into direct metal 3D structure. You can see that's how the performance looks like, and using at the different conditions, cast aluminum bronze, wrought aluminum bronze, and cold spray aluminum bronze, compared with the heat treatment, also heat treated aluminum bronze. So again, sorry, I think I went too quickly there. So these are some of the, again, different properties that can be achieved. Again, what I'm trying to highlight here is, as you can see, the properties, if you can heat treat the cold spray additive manufacture part, especially with aluminum bronze, what's shown here, it can achieve close enough to the wrought properties, so which is good enough here. And again, it's better than the cast aluminum bronze, also far more better than the cast aluminum bronze properties. And another thing is, very important thing is, we talked about the different process parameters of the different conditions that impact. Again, the powder particle raw materials I spoke earlier. Again, this powder particle was a low-cost powder particle achieved by ball milled. And again, powder particle, when you think about 3D printing applications, you'll always talk about spherical powder particles. But cold spray doesn't need to be spherical powder particles. Different shape is also fine because you're more looking at the flowability of the powder. However, sometimes in the nozzle, what you're looking here, the nozzle here, you can see that it can get clogged also. So you have to be very careful when you do the printing. So the deposition efficiency will determine how far. So if you're putting a 1 kilogram of powder, if you're getting 800 grams of a part and 200 grams might go off, that's really good deposition efficiency, you would call. But if you're achieving anything less than 50%, that's not really good. So what we did is, again, the low cost powder feedstock, we got it, and when we used it, we achieved a significantly very high compared to other people who have done work in this area, close to 60% deposition efficiency, which is really good for a low cost aluminum 75 powder, the 7000 series powder. And so optimal conditions are identified, and we printed the parts. So this, again, probably a lot of people know aluminum 75 is far more better compared to 61 alloy. And this is used quite a lot for a number of different applications, high strength applications, I would say. Again, this work focused on metallic thermal interface. Again, I spoke earlier about regarding to the interface with the ceramic tile interface. We looked at the joining and bonding mechanism here. So adhesive strength also, we looked at the copper on top on the ceramic tiles. So we can see you can have different grooves or different substrates. And again, you can see also here how much copper particle is embedded into the substrate. This is the cross section or side view of the ceramic tile. Again, we looked at the thermal conductivity point of view, how the properties looks like, mainly the sustainability point of view. Air-based cold spray offers low energy route to copper nickel thermoelectric material. So this one is a copper nickel material here, combination of copper and nickel together, which we used for, again, to try to study whether it gives far more better property than the copper itself, using copper alone. And again, this work was mainly focused on the interface substrate, how the interface bonding or surface bonding can happen with the ceramic tiles with the interlocking mechanism. So as you can see here, with the different interlocking mechanism, you can get a better bond strength. And again, at particular condition, it achieves so far more strength compared to other process. So this is a part, again. So most important thing is, obviously, all these studies are vital for us to understand what are the properties it might achieve or what we might get during the cold spray process. Again, this is another part just to show you nose cone. Oops, sorry. I think I might. I think the slides might have gone. Just bear with me.
Yes.
Just bear with me.
And while that happens, maybe a quick question of the
Sure.
powder particle size.
Yeah. So we use around like 50 to under 80 microns, some cases, or 20 to 50 microns also. Just a minute here. So few different ranges are used, powder particle size are used. Again, depending on the machine type and also the process type also. That's a different range are used, but most commonly 20 to 80 micron range is the 60 micron range is a common range.
Perfect. Yeah, we see the video running.
Sorry, can I see the video running? Sorry.
Yes.
Okay.
We were running. Yes.
All right. Okay. So that's what, just to show you that the three-dimensional part, how it's been built, and you can see this is the finished part, machined part section. And again, different shape. So it's certain geometrical limitations might be there. So still you have to machine the sections once after 3D printing. You have to machine the sections, but it's not always completely possible to incorporate internal channels or internal structures, some cases with the cold spray. It's not like SLM or laser DED process. And again, metal matrix composites, I spoke again a while ago, that's same thing. printability of thermal electrode materials with different combination. This is again CSAM or scanning electron microscope images that's shown here with different materials, like looking at metal matrix composite of different material type, which can improve the properties, especially thermal electric conductivity, far more better. Again, this is another few different material types here, again, to show you. So the thermal interface, as you can see here, which is again the substrate changes. You can see how the particle bonding is happening with the surface substrate changes. You can see here how much the copper particle has gone in between the grooves here, how much bonding has happened is shown again. So this is the work which was extensively studied for a number of years in this particular case. Again, a few more of this copper nickel material, thermoelectric materials shown. And again, this is currently in the process of published in the process of publication, I would say. And again, I spoke about this also earlier. So another important critical factor is reproducibility and repeatability point of view. That is one of the very critical factor. That's why we've done extensive studies. As you can see, 55 stencil test coupons were studied, and how much better properties are achieved over a period of time. It's very important. That is one of the limitations of additive manufacturing, I would say. And again, as you can see, the powder particles varies also. That might be changes in the properties also. So that is why it's always you have to make sure the product you make, or the process in which you achieve, that is reproducibility and repeatability is happening up to a certain level. Because in SLM process, you can recycle the powder for a number of times. Once you recycled after a few times, then you cannot go beyond particular time periods. So that is very important to understand the limitations, how many times you can recycle. Similarly here also, the powder particles, even though you cannot recycle much, because it's usually captured or exhaust through the wet extraction system or a compressed air system based, you will extract the powder particles. You cannot reuse the powder particles always here. So you have to be very careful achieving the deposition efficiency and also making sure the parts can be reproducible in particular condition. So this is what I talked about, the aluminum 7075 material, and also how the particles looks really different. Powder particle looks completely different to the powder particles you see here. This is completely different to this powder particle type. Still, you can able to print the parts with the cold spray process. However, no way this can be done with the SLM, because you cannot have the powder particle cannot be pushed on the bed that easily. So we are also looking at, I've got only a few more slides to go. So I'd like to finish off soon. Mainly what we are also looking at, all this work, extensive experimental work is done. We are also looking at the modeling aspect, which is very critical, so that you don't spend too much time on doing the experiments and breaking the parts, tensile test and everything. So modeling is very, very critical. However, the challenge is most of the modeling work that is being done were focused on up to the nozzle end, because where the gas particle is propelled and how fast is coming, what kind of temperature is achieved for different material type. So quite a lot of work is focused on the nozzle. But when you come to the deposition, because it's challenging to get a multi-layer deposition, you need extensive, work to be carried out. And even achieving this 10,000 particles, it will take days and days of computing power. So even the work which we done, we performed an high performance computer, which is like supercomputer, and it took even with that, it takes quite a bit of time. But however, it reduces time by significantly, 40% of the time compared to the normal time in the normal computation. So it needs extensive computing skill process. So this is an example of the work which they carried out by my student, and the particle deposition, 10,000 particle deposited on a substrate. It gives an idea how much particles embeds and how many particles bombards from the substrate based on because you got different mass, because each particle is different size or different shape kind of thing. And then it carries different mass, obviously different velocity it propels at, So it creates a different bonding mechanism and also bombarding it also. As you can see, this is the coating thickness achieved. And as I said before, even using the high performance computing resources taken 63 hours just for a small layer of 441 micron layer thickness. Small layer thickness, 441 micron layer thickness. It took 63 hours of supercomputer to do the simulation. And
Interesting,
again,
Dr. Suresh. Uh,
sorry.
but there were a couple of questions on this as well. So, is this a tool that's developed by you, or are there any commercial tools available that people can get access to?
Unfortunately, there is no commercial tool right now available. That's what we are working on with our collaborator CSRO. And
Mm-hmm.
so, like CFD, a lot of CFD flow because it involves both, how to say, kinetic, powder flow particle kind of thing, and also it involves materials bonding materials process also. There's no specific software that
Okay.
ANSYS has been used or Abacus can be used here, but
Right.
still as you can see, this work was done by the
Yeah.
student, and you have to write a separate Python code, automation code. So we're
Mm.
hoping to, if it is really feasible, we are trying to do furthermore evaluation and testing. If it is
Okay.
feasible, then probably we might look to commercialize ourselves. So this is very important finding because, as I told you, achieving this layer thickness, it's
Mm.
very hard, multi-layer thickness. People have done one layer or two layer maximum, not this much layer. And maximum what we have seen in the literature so far is 400 particles or something like that. So we
Mm.
achieved 10,000 particles. So which is a significant number of particles
Mhm.
deposition. So that shows how difficult this work is.
Right. So I do see, residual stress on your slide here, and there is a question on that as to how it compares with other additive technologies.
Yeah.
We have about 8 minutes left, Dr. Suresh, and we have quite a few questions which seem to be in the direction of comparison, as in how does it compare to, EBAM or other DED process, also, uh, comparison in terms of material properties. So
Yes.
maybe as you go forward, you can also try to answer some of those
Absolutely,
questions.
no problem. So what I'll do is again next few slides are just few examples. I like to show just for a
Hmm?
reference where it can be applicable in the cold spray process. But again, the residual point of view, see again, you're not inputting too much heat. You're not using like a laser or EBA electron beam kind of thing. So the residual stress still will be there, comparatively far more lesser than the SLM or other process, I would say. But still, the residual stress will be still there because still you're trying to creating the powder particles embedded together. So residual stress, like bonding, the mechanism in which it's done. So still the
Mhm.
residual stress will be there. You can see. So that's why this particular case, uh, the work is being focused on how to estimating the porosity in this deposition process and also getting the residual stress values also through the modeling work. So this is significant work has been done here, and we are trying to expand this work furthermore for different material type. So
Sure.
just again, few of the material. I think somebody was asking about tool steel. That's what I was mentioning. So this is the part we printed with the stainless steel 316 material. Uh, so this was done. And again, for example, this is one of the application actual part that's been replaced. This is the damaged part, as you can see here. That's damaged part, and it's in the field trial. It was taken to a remote region in Australia. When I say remote, is really remote. You won't see for thousands of kilometers. Nobody will be there. That kind of place, and the whole machine and everything is taken to the remote region. And then the army people printer. They had the heat treatment facility and CNC machine also. They took with them, and they did the finished part there, and obviously retrofitted. When this kind of situation appears, when they are in a remote region, we cannot able to get access to the replacement part or anything like that. You can print the parts directly. And again, multi-material application. In this case, again, you can see a pure copper liner is being used. Sometimes you can multi-material can be done also. Inner layer or layer part can be different, and outer layer part can be different. In this case, copper is being used here, and printing time is 3 hours 90 minutes. So this is one of the key comparison, I would say. One of the graph I showed you earlier, the compared to powder bed process or EBM process, the speed is high, really fast, I would say. No way this can be printed in 3 hours. It will take days to print in a powder bed process. And DED might be a little bit less time or quicker compared to the powder bed, but still it won't be fast enough than to the cold spray process. Only thing which is far more advanced, like speed wise, is I told you, additive friction stir deposition process. That's far more faster than this one because the speed is very quick in that case. Here you achieve a higher speed. However, the trade-off is the properties. You have to trade off the properties because of speed. Again, this is also another example. That's the damaged part that has been replaced with a short time period, and it's been the print time is 12 hours. Material is aluminum. It's done very quickly in a sense. So there are quite a number of interesting work. I think, again, somebody asked about multi-material. So advanced embedded particle type, different particle type, how to look at it. So there can be research work going on here. Multi-powder feeders can be done. Also look at what is going on this particular area also. And also substrate topography, which I talked about briefly, having different substrate type, and also the post-treatment techniques. There's, again, quite a few different heat treatment techniques are there. Hipping can be done, and obviously sintering of different methods of sintering can be done, and obviously using vacuum furnace to heat treat it. Electric sintering, electric heat treatment process also, we're looking at it. One of my colleagues is looking at that also. So that's different mechanisms of post-heat treatment techniques also there. So these are the key areas to focus for the further deployment or growth of this particular technology. So finally, this last few slides, just another application to look at is we're using low-cost powders or recycled powders in this particular case to mitigate corrosion. So the substrate is titanium material. Sorry, titanium powder particles are used on a steel or mild steel substrate because this is for a building industry sector. To avoid corrosion, we use titanium to coat the titanium on a grit-based steel, as you can see, and different properties can be achieved. And corrosion resistance, as obviously most people might know, titanium far more better in the corrosive environment. So that's why we are trying this with the low-cost powder also, with the different post-heat treatment conditions in this particular case. So consider the time factor. Obviously, I like to acknowledge the team. Quite a number of people are there, and again, no one is here today. And I think that's my postdoc with my PhD students who've done quite a lot of work, and also my collaborators from India, and also from a number of industry partners are here. Finally, thank you.